I will begin. Dearly Father, we thank you for this day. Again, Lord, I thank you for these students. Just ask you to bless this class, Lord. In your name I pray. Amen. So, there we go.
Which direction am I supposed to read it? You should do this until that's not a good idea. Stop. I would have like a 0 per person. That's a bad idea.
Wait, why are you saying that's a bad idea? I think it was when you noticed it. I just noticed that it was a cool pattern. Or, I mean, I just...
Oh, I thought you were agreeing with solving for the top hat number. That's a bad idea. I promise I will not.
Morgan is absent for every single class.
Even though I do.
She just refuses. She's
No,
like,
I
no,
just-
I'm not going to do
This is what I do. I wait to watch Bethany. What's that I can't read the book. Sorry. I got my contacts today. Yeah.
So this is Theorem 6 in section 10.3. For any set A, there exists a free R module, f of A, on A, and it satisfies the following universal property. And so here's the universal property. If you have a map from A to M, all right? If you have a map, and here M is an R module, all right? Then if this is a map, then there exists a unique R module homomorphism that's phi, big phi, going from the free module f of A to M, such that big phi of A is equal to little phi of A for all A and A, which is to say that the following diagram commutes. So you've got A, you've got inclusion into f of A, and you got the map that's given down here, phi, going to M. And from f of A to here, you've got the big phi. So this is inclusion, which I usually use a iota, I-O-T-A. It's like an I without a dot. It drives me nuts. It's all I can do to not put a dot on that right now. But yeah. And furthermore, when A is a finite set, all right, if A is a finite set, so the diagram commuting, what that means is that you could go with this, or you could go with that. So you could go this, or you could go the other way, right? So the red would be phi composed with iota, and the other one would be the little phi. These are equal. That's what the diagram commuting means. Again, so if A is finite, if A is A1, A2, AN, then we have more. Then f of A can be written as the direct sum of cyclic R modules in the following sense. F of A would just be RA1, direct sum RA2, direct sum RAN, like that. Which, of course, is isomorphic to the Cartesian product of the ring in question n-fold times. So what does it mean to say that this R module f of a is the R module f of a is free on A? What's that mean? That means that A serves as a linearly independent minimal generating set. In other words, the R span of the set A gives you f of A, and you can't, it's the smallest generating set that's possible, all right? That's what that terminology free, all right, means there. So this is the theorem. It's kind of, I would say it's kind of breathtaking if you just look at it. Like, I mean, which set? Any set. Any set you can build an R module, a free R module, like this. How on earth are you going to prove such a thing, right? Well, let's look at the proof. If I can find a marker. Yep.
So is it like saying that the span of a set is a vector space, but just in general?
Is it like saying the span of a set is like a vector?
Is it
Yeah, it's like that, except, when we start with the thing that's really, really different about that thing that you're bringing up, that like the span, you give me a set of vectors where? You're telling me, give me a set of vectors inside a vector space, right? Like in linear algebra, did we ever say, take a set of vectors, they have no home, right? That's what this is. This is starting with a set in the wild. It's not like a subset of a given module. It could be, but that's not what this is. This is just an arbitrary set. We're going to build an R module structure for it from scratch. And that's very different. But yes, analogy would be the spanning theorem for linear. Totally agree. So here's the deal. Here's the proof. He says f of a, you can just set it to be 0 if A is the empty set. And here, this is the 0 in the ring, right? So pick your favorite ring for this discussion, all right? It's got a 0 in it, and that will serve as a free module in the case that we have the empty set. All right, that was not exciting. All right, so on the other hand, if A is not empty, then let f of A be the collection of functions of the form f mapping from A to our ring. All right. The choice R is fixed here in this whole discussion. Again, we're fixing a particular ring and doing what we're doing. All right. So the set of all functions such that, and what's the string we're going to attach? Such that f of A is equal to 0 for all but finitely many A and A. So they're functions which are mostly 0, if A is infinite, right? Of course, if A is a finite set, it could be non-zero in the whole set. That wouldn't violate it, right? Yeah. And then what he says is we'll make f of A into an R module by pointwise addition of functions and pointwise multiplication of a ring element times a function in the natural sense. So, definition, f plus g of A is equal to f of A plus g of A. And, a ring element times f of A is equal to R f of A. This is for all A and A, right? Observe f and g in f of A clearly implies that RF and also F plus G is again in F of A, right? Why? I mean, just think about it for a second. If F of A is only, you know, if it's 0 for all but finitely many A and A, then so is R times F of A, right? And likewise, if we take a sum of things that are mostly 0, then there's no way you can take a sum of two things which are 0, which are non-zero at a finite number of places, and somehow add them together and get 0 at infinitely many places, right? I mean, non-zero at infinitely many places. So it's fairly clear that it's closed under these operations, right? And then to prove that F of A is a ring in our module with respect to this addition and multiplication, it's pretty straightforward from here, right? What do we have to check? We should check what that it's that's an abelian group with respect to the addition. But that's going to be the case because the addition is happening in the ring, which is commutative, right? We can just define the negative of the function to be the function which takes negative values of the given function, right? They add together to give us the 0 function. The associativity that you need and the distributive properties are all going to follow because these are taking their values in the ring itself. And so in the ring, we have the distributive property. And so that will transfer through to this definition, to this set F of A, right? Now here, what comes up next is a little bit less sneaky, well, a little bit more sneaky. He says we can identify A as a subset of F of A. How are we going to do that? By A maps to F sub A, all right, where, what's the definition? F sub A of B is equal to what? Zero if A is not equal to B. And what? Remember, no. The output of F is in the ring. A doesn't have to have anything to do with the ring. A could be a set of cats, chickens, seafaws, whatever. Sorry, let's not bring seafaws into it just yet. So, I mean, I guess you could do a lot of different things, but one is what Dumb and Foot has. It's the characteristic function. It's like, okay, it's going to be 1 if they match, and otherwise it's just 0. It's kind of a generalized Kronecker delta. Is that in F of A, big F of A? It's mostly 0, except for that one spot where it's not, right? And he points out that, he says, in this way, we can think of F of A as all finite R-linear combinations of elements of A by identifying each function F with the sum R1A1 plus R2A2 da plus Rn where F takes on the value R sub I at A sub I and is 0 for all other elements of A. Moreover, each element of FA has a unique expression as such a formal sum. To establish the universal property, let's see here. So I think he's saying that this R1 A1 plus R2 A2 z plus Rn An would of course then correspond to which function? Just R1 FA1, right? R2 FA2 Rn Fan. This function behaves as that element. Oh, anyway, so to establish the universal property of f of a, suppose we have a set. Suppose we have phi, a mapping from where to where? From A into M, where M is an R module. So we have a map. He says, so we're going to have to define, we're supposed to define the big phi from f of a to M. How are we going to do that? What's a typical thing in FA look like? Why is it that this is typical f in big FA? Why is it that any function in this FA can be written as a linear combination of characteristic functions of a finite set of elements from A? A could have infinitely more things. I'm just saying there exists, I mean, remember that's the definition of FA. It takes on finitely many values. So look at those set of finite values. The set of values would be what? R1, R2, Rn. And if you just take those and multiply by the characteristic functions where those values are being attained, namely A1, A2, An, well, that's a formula for f. The fact that such a formula exists for any function is just by the construction of f of a itself, right? It takes on finitely many values. So you pick those values, R1 through Rn, which are being mapped to from the inputs A1 through An, and that's a formula for f. So that's a sort of generic element in f of a. So to define phi going from f of a to m, I need to say what happens to that, right? So this is like typical f would be R1 f of a1, Rn f of an. And I need to do what? I need a, what should that be equal to? I have the little phi to work with, right? So, and I need the output to be an m. It pretty much forces you to feed the a's into the little phi and then use the r's as weights. So what you're going to do is just R1 like phi of a1, Rn phi of an. This expression makes sense because m is an R module, so we can left multiply by ring elements. And the fact that that makes the diagram commute, I think, is immediate from the construction that we've done here. Oh, phi is a what? It's an R module homomorphism. What can I do with the r's? Yeah, I think I can do that, right? Yeah. Oh. Well, I don't know if I can actually, because then, well, I'm sorry, I'm overstating my case here. It's an R module homomorphism from f of a to m, right? So if I had like yet another ring element out here, let's say S, right? Then that would put an S on this whole thing, right? Which would put an S on this whole thing. We'll put, and then that I could actually rewrite as S phi of f, where this is phi of f again. I don't think I actually have a definition for the ring acting on A itself directly. That's kind of what I was scratching at the start of this discussion. A is just a set, right? But, yeah.
What
phi that's going, that is a given map. So this is just a map, a function. That's all we get. That's what I got my phis confused. Little phi, I do not have I can pull r inside of it rule. It's just a function. It's the capital phi, which we're constructing, that should be an R module homomorphism if we did our job.
So phi of A1 is F sub A1?
Phi of, which phi are we talking about? Okay, the sideways TIE fighter. So phi of A1.
No, wait, no. I'm talking about the top one.
Oh, what is phi of A1? That one? Yeah, I don't know. It's just it's an element of M. To be picky, this doesn't make sense either. All right? Because is A1 in F of A? No, but it is if we allow ourselves to think of A1 as being F sub A1. Like this, technically speaking, makes sense because F sub A1 is in the F of A. It's something that has, it's 1 when the input is A1, it's 0 otherwise.
So how do you know that you can go from that top equality to the next line?
Here to here?
Yes.
I suppose I don't. Let's see here. That's a good question. Well, let me tell you what, let me erase the S here for a second. And this is the question, right? So what I have right here is the definition. This is the definition of the big phi, right? We need two things for that to be an R module homomorphism, right? We need that it's additive, and we need that we can pull out the ring multiplication. Do you see why it's additive? Like if you took phi of F plus G. Right. I mean, this is awful, but here you go. This is something. F has something like R1 F of A1 plus Rn F of An, right? The G would likewise have, let's say, I don't know, S1 G of B1 plus plus SM G of Bm. There exists a set of ring elements and a set of characteristic functions which describe the action of G. It has finitely many non-zero outputs. And then I guess technically I should ask myself the question, then at this point, by definition, that is, R1 phi of A1 plus Rn phi of An plus S1 phi of B1 SM phi of Bm, because that's how we define the big phi. It's the ring linear combination of the images under the map of the elements in A which produce non-zero outputs for our functions. And then what do? You go, well, that is exactly, that's exactly phi of R1 F A1. Oh, I think I'm going in circles. I guess at this point I should go that this piece right here is, coming from this, right? Well, let me just get to the point. this piece is phi of f. This piece is phi of g. So, I mean, getting into the nuts and bolts of this theorem requires like taking a function that has finitely many non-zero outputs and like writing it in terms of the characteristic functions and then messing with them to see the property. I mean, that's...
So you're defining the big phi of that thing just to be, like, that's a definition?
Yeah, this right here is the definition, right? Going from here to here, definition. Fair enough, yeah. My point is that definition is general because any function in f of a has such an expansion, right? And the proof that we could pull the ring multiple out is pretty similar. All right, so there you go. That's how we can build a free module for any set. The remaining claim that, you know, it's just this, you know, what's left to prove there? Well, he says, I mean, here's what he says. He says, when A is a finite set, proposition 5, part 3 shows that f of A is the direct sum of these. Since R is isomorphic to R times AI, under the map R maps to RAI, proposition 5, part 1 shows that the direct sum is isomorphic to Rn. So this is the independent subspaces result that I mentioned last time. But so corollary to this, corollary 7, says the following. If F1 and F2 are free modules, all right, on same set A, all right, then there exists unique isomorphism between F1 and F2, which restricts to the identity on A. So I'm pretty sure going forward, guys, whenever this construction is referenced, we're going to take the viewpoint that A, like this, in future sections in Dummett and Foote, when this is used, they're going to take this arrow and make it into an equality. We're just going to say that these maps are really what A is. No.
Does that say same or some?
Same set A. But it could have just, you could write some. It wouldn't be, it would be the same meaning. Sorry. F1 and F2 are both free over A, is the point. They're free on A, and A is some set. And then point 2 here is that if F is any free module with basis A, then what? Then F is isomorphic to the free module over A that we just constructed, all right? In particular, he says F enjoys the same universal property with respect to A as F of A does in our theorem 6. Furthermore, comment, when R is equal to the integers, all right? When R is equal to Z, then F of A is the quote-unquote free abelian group on A. He says, if the cardinality of A is n, then f of A is called the free abelian group of rank n, and it's just isomorphic to z plus z plus z plus da 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 plus z. So, if the size of A is equal to n, then f of A is up to isomorphism, just z plus plus da 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 plus z. Yep.
I could have just missed this, but what exactly do you mean when you say the unique isomorphism between the two free modules restricts the identity of A?
So that's with the understanding that we're making this inequality. Because it's, f, so f, we have, so essentially that says f1 is the span, well, what it is in the notation we used last time, f1 is RA1, f2 is RA2, right? If they're free modules, right? So they're generated by A1. Oh, where's A1 and A2 coming from? Good grief. Same A, right? You guys told me already, same A. If I could just, not invent extra indices where there are none. So if it generates both F1 and F2, right, then there's a map, let's say psi, from F1 to F2, and psi restricted to A is equal to the identity on A. Because A is a subset of F1 and A is a subset of F2.
So the isomorphism does not cover the whole sets. A is a subset of F1 and of F2.
Right. Well, I mean, A is not equal to F1. A is not equal to F2. F1 and F2 could be much bigger. I mean, A is like a basis for F1 or a basis for F2.
Right. So that isomorphism is the size. Yeah. So I guess its domain is A, right?
Yeah.
Or its domain. Yes.
I mean, to be fussy,
Or it's the size of A.
and also to be fussy here, A is actually a subset of F1 and F2 in contrast to the construction over here where we started out with A in the abstract. And then we replaced A with characteristic functions corresponding to A, which then allow us to interact with the ring in a natural way. So I don't think you really appreciate how weird this is until you put it into practice. Take the desks in this room. How many are there? 1, 2, 3, 4, 5, 6, 12, 18, 24, I don't know, 30. There's like 35 desks in here, right? You could build the free abelian group of rank 35 by taking integer linear combinations of these desks. It would be meaningful to add and subtract these desks in this abstract space. You guys don't care. All right, well, anyway, I think it's done. Why, indeed. I will show you that next week, actually. Yes?
If they're generated by the same set, why aren't they the same? Like, why isn't F1 equal to F2?
I think that's because of the way the ring would interact with the, it must be the way the ring interacts with the generating set.
But it's the same ring, right?
Right, but it doesn't have to be the same R module. The ring could interact with the set A in a different way in F1 and F2.
So it would be like multiplication versus addition, or I know it probably wouldn't be that. I'm probably misunderstanding something here, but it'd be analogous to that.
I don't know. I have to think about it to come up with an example for you. That's kind of like off. I don't know. You'd have to let me think about that for a while.
R's, the F1 equals RA.
Yeah, the same. R is fixed throughout this. We're talking about R modules.
A is also fixed.
Same A. Yeah.
Is R an R module or is it a ring?
R is a ring,
A ring.
but it's also an R module with respect to itself. I knew you'd not appreciate that add-on, but.
Not really.
But it's true. Okay, moving on, moving on. So,
Last question. F1 and F2 would both have the properties of an abelian group, of additive, right? It would be an additive.
they are both additive abelian groups, right?
Okay, but they would differ in how they interact and how their elements interact.
That's what I think. Right, right. I have nothing more to add there at the moment. I'm sorry. I don't know if I've really addressed your questions or not, but you'll have to forgive me. With that, we go on to section 10.4. Now, in yesteryears, I have at times become sucked into starting, and there's like the first 4 pages of section 10.4 are all a special case, but a general special case, which is lovely, but I actually want to get to the point here and not spend all of semester on tensor products. So let's just get right to it. Here's the deal. M and N are modules. All right? Then you can look at M cross N is a Z module. Right? Because any R module is a Z module, right? We can always look at an R module as a Z module. That's there for us. Okay? So certainly the Cartesian product of M and N is itself a Z module. Now, the idea of section 10.4, let me just give you a little bit. I'm not going to give you 4 pages of motivation. He does. This is on M tensor N. And basically what we're after here is a way to take 2 R modules and put them together in such a way that you can multiply elements in some kind of abstract way. And you want to be able to multiply elements in the way that you'd expect. Like this multiplication, if you had 3 things, it should be associative. It should obey sort of natural distributive laws. And all those things turn out to be true. All right? But first things first, how do you actually construct M tensor N over R? The answer is really kind of neat. So what you do is you look at a quotient module. You take this M cross N and you quotient by submodule generated by relations. So what are the relations that we're interested in? M1 plus M2, comma N, minus M1, comma N, minus M2, comma N. Let's see here. Also included are things like M, comma, N1 plus N2, minus M, comma, N1, minus M, comma, N2. And last but not least, MR, comma, N, minus M, comma, Rn. These are all in, let's say, R, the relation submodule. So if you look at objects of this form, right, built from arbitrary M1, M2, M and N, and if you think about this, if you put these things together, you get more things like this, right? If you add these, you get the same. If you were to multiply by an integer, you would still get relations of the same form. We could check the submodule criteria for this relation submodule. It is an honest-to-goodness Z submodule of M cross N. Therefore, I can form M cross N mod R by the quotient submodule construction. Is a Z module. And here's the deal. We write M comma N plus R, right? That's an additive coset in this Z module. We don't write that. Forever on from past this point, that is expressed as M tensor N. So M tensor N is an equivalence class mod these relations. What do these relations mean for the tensor product? Because remember, the quotient makes the things that are in the quotienting object be essentially 0 in the quotient, right? It's an additive quotient. So these behave as 0. So what do these different relations mean? By construction, what do we have? We have like M1 plus M2 tensor N is equal to M1 tensor N plus M2 tensor N. Now I wrote it as an equality rather than equals to 0 because I think it's more interesting that way, right? Do you understand my point? I mean, if you just kind of directly read this, it would give you that M plus 1 tensor N minus M1 tensor N minus M2 tensor N was 0. But I think it's better to think of it that way, yeah. And how about the next one? This would give us M tensor N1 plus N2 is what? Indeedly. See? You understand tensor products? I knew it. I'm wasting my time. And then how about the last one? That says that MR, parentheses, MR tensor N is equal to M tensor Rn. So by construction, the tensor product of R modules M and N have this algebra. All right? Now, he has a, yeah.
Okay, the R in, when you say by relations in R, is that the ring or is that something different?
Different than the ring. This is a submodule of the Cartesian product of M and N.
Okay. R is a given submodule of n cross.
It's the span of all such things as this. Yeah. So, definition. If we have, we can let M be R, what's called an RR bimodule. It's an RR bimodule by RM equals to MR. And so if you're given a left or a right R module, you can define respectively a right or a left R module structure by just insisting that the multiplication commutes like this. So if you start with the left, you can get the right. If you start with the right, you can get the left. Put this all together. This is the quote-unquote standard R module. This gives M the standard R module structure, as it's called. So this shouldn't be altogether unfamiliar. We did this in linear, right? Sometimes we multiply on the left, we multiply on the right. Pretend like we actually define this. I usually just start doing it, never really talk about how to define it. But that's it. Now, just like there's a universal property, for that free module, there's also a universal property for the tensor product. And here's how that goes. And I know that when I say universal property, you have no earthly idea what I'm talking about, and that's okay. That's one of the things we're hoping to gain a sense of, if nothing else, by kind of just soaking in it for a while. Eventually it might stick, I'm hoping. Anyway, so first of all, definition. If we have R as, now we're specializing a little bit, R commutative ring, all right, with 1. And we have M, N, L, all R modules. Then we say phi, a mapping from M cross N to L, is bilinear, or R bilinear to be more specific, if it's R linear in each factor. In other words, phi of R1 M1 plus R2 M2, comma N is equal to what? R1 phi of M1 comma N plus R2 phi of M2 comma N. And likewise in the other component, right? Like phi of M R1 N1 plus R2 N2, R1 phi of M comma N1 plus R2 phi of M comma N2. If you had bilinear, this is familiar. We talked about bilinear maps, at least a little bit, I think. All right, so that's a bilinear map. This is the universal property then. Here's corollary 12 in a nutshell. Here's what it says. It says that you can either talk about R bilinear maps phi going from say M cross N to L. There's a direct correspondence between R bilinear maps on the direct product of M and N like this, or R module homomorphisms say phi going from M tensor R N to L. In particular, the correspondence is given by the following commutative diagram. So we do M cross N, and you got yourself the iota, M tensor Rn. I got my L down here. My bilinear map phi goes diagonal, and my R module homomorphism goes vertical like that. So, now, I neglected to write. So this is where you got to decide: is it worth it, notation-wise? Technically, sometimes we throw in the. So this would be actually M tensor R N. Whether or not you adorn the tensor with the ring which is being used as the base ring kind of depends on what level of detail is needed for the given conversation. As you can see, it's been used here in this statement of corollary 12. This adding the ring in question is because you could talk about a tensor product over the integers. You could talk about a tensor product with respect to the reals. You could talk about a tensor product with respect to the complex numbers. Which ring you're taking as the base ring matters. The reason it matters is if you're working with a tensor product over the integers, that means that you can move integers freely like in from one side of the tensor to the other. If I was working with a real, if it was like a tensor over the reals, I could move real numbers past the tensor, right? But I couldn't move complex numbers past the tensor if I was working with the real tensor product. See, R has to be in the ring to have these identities, is my point. We'll talk more about that next time, okay? But listen, the long story short here is just that this is a really nice theorem because it means we can check whether or not a mapping is a R module homomorphism on the tensor product by simply checking for bilinearity on the Cartesian product, which is a kind of simpler thing to think about. Because as we'll see next time, the actual, what do tensors actually look like and how do you study them, it has some nuances. But what I'm trying to do right now is to give you the high points of section 10.4 and not get bogged down in the dozen pages of technical background. We want to get to the main points, which are towards the end of the section. And so next time I hopefully will cover some of the examples on page 368 and 369. And I will just state without proof, theorems 13, 14, corollary 15, corollary 16, theorem 7. I mean, I'm not sure I'll even state them. I may just read them. So, I mean, our goal is just to gain an appreciation for the rest of the section next time, and also to talk about the antisymmetric and symmetric tensors. Those are something past this, which is actually kind of simpler in its own right. All right. But anyway, I shut up.